Kinetics. Spontaneity determines if a reaction occurs as written. Kinetics, on the other hand, are concerned with the rate that a reaction occurs. Gallons per minute, miles per hour, both are rates. Usually, for reactions, reaction rates are measured in molar per second. Similar reactions, which can both be favored, can occur at different rates. For example, rust versus combustion of iron occur at two different rates. One occurs very slowly, the other occurs much more rapidly. A reaction may be spontaneous, but have no measurable rate. The reaction of hydrochloric acid with magnesium hydroxide has a delta G of reaction of negative 97 kilojoules per mole. The reaction of diamond with oxygen has a delta G of negative 397 kilojoules per mole. However, the first reaction occurs quickly, but the second reaction has no real discernible reaction rate to it. Reaction rates are measured in moles per liter second or molar per second. We can measure the rate of a reaction if we know a way of measuring the concentration changes and we have an equation for the chemical reaction. For example, the compound dinitrogen pentoxide produces nitrogen dioxide and oxygen gas. If we can measure changes in the compounds, for instance differences in partial pressure, we can monitor the rate of the reaction. This method allows us to describe the rate versus the change in compounds. Rate is going to be equal to the change in the concentration of a reactant or product with respect to time, or delta concentration with respect to delta T. For example, the generic reaction little a, little b, b, going to little c, plus little d, d. The change in the reactant A is equal to the negative, because it is decreasing as a reactant, delta concentration of A divided by delta concentration, or delta T. So the change in concentration of A with respect to change in time. A certain number of moles of A exist in each mole reaction, represented by the little lowercase a. So 1 mole reaction contains little a number of moles of A. The overall rate of the reaction monitored by A, then, is the rate is equal to negative 1 mole reaction per A moles of A times the change in concentration of A with respect to T, or negative 1 over A times delta A over delta T. For any reaction, we can compare the rates of a particular compound to any other compound in the reaction. For our generic reaction, we can compare A versus B versus C versus D. Negative 1 over A times the rate of A would be equal to negative 1 over B times the rate of B, which would be equal to 1 over C times the rate of C, positive because this is a product, and 1 over D times the rate of D. Any of these individually would give us the rate of the reaction. For the example dinitrogen pentoxide that we have here, what is the rate of formation of NO2 versus O2? There are 4 NO2s and 1 O2 in 1 mole reaction of the reaction. So 1 mole reaction per 4 NO2 equals 1 mole reaction per O2. Going from NO2 to O2, then, the rate of the NO2 with respect to time could be able to be multiplied by 1 mole reaction of oxygen per 1 mole reaction per 4 moles of nitrogen dioxide, which would allow us to have a 1/4 rate times the rate of the nitrogen dioxide. So our oxygen is produced at 1/4 the rate that nitrogen dioxide is produced. The rate of the O2 formation can be measured then if we know the rate of the NO2 formation. If, for instance, NO2 forms at 0.0072 molar per second, what rate does O2 form? We have the rate of the NO2 formation at 0.0072 molar per second. The rate of the O2 then would be 1/4 the rate of the NO2, or 0.0772 molar per second times 1/4, giving us 0.0018 molar per second. We can monitor a rate by the change in the product increasing or the change in the reactant decreasing. As time gets smaller, the difference between the final time and the initial time approaches a single point. We can calculate the single point from the derivative of the change in the reactant. Negative 1 over A times the derivative of A with respect to T. We can from this plot an initial rate from the slope or negative slope at T equals 0. We see at the initial slope at the time equals 0 gives us a rate of the reaction initially. We can also plot the rate at any time t, or what we call the instantaneous rate, as a tangent to the curve at that time. Here we see a tangent line drawn to the curve of the reactant, where the change in molar versus the change in time as an average meets a single point on the line. The smaller the delta t value, the more accurate this is going to be, because it's going to be over a smaller period of time and gives closer to an actual derivative rate. Factors affecting rate. We need the reaction to be fast enough for us to use, but slow enough for it to be used safely. Iron rusting occurs very slowly. However, the combustion of isooctane gasoline is useful to us. If we increase the rate in isooctane combustion, we can get an explosion, which is dangerous. Some reactions we need to slow down. For instance, the spoiling of food occurs because of specific chemical reactions, and we want that to slow down, so we find ways to slow that reaction. A reaction rate is affected by 4 factors: the nature of the reactants, the concentration of the reactants, the temperature of the reaction, and the presence or absence of a catalyst. The state of a reactant can affect its reactivity. For instance, liquid gasoline is an effective tool to use because its reaction is more controlled. Gaseous gasoline is explosive in its reactive rate. Immiscible liquids, those which don't mix together, react at the interface between the 2 liquids. Mixing the liquids together will increase the speed of the reaction. The arrangement of a substance also causes it to react differently. For instance, graphite and white phosphorus tend to react relatively quickly. Diamond and red phosphorus, on the other hand, have no real discernible reaction rate, where diamond obviously is a form of carbon like graphite, and red phosphorus is a form of phosphorus like white phosphorus. Oftentimes mixing solids together has no discernible real reaction rate. However, if we make solutions of those solids, they tend to react well. Potassium sulfate can react with barium nitrate to produce potassium nitrate and barium sulfate. If I just mix those as solids, they tend to do very little, but mixing them as solutions will give a fairly effective reaction with the precipitation of barium sulfate. The identity based on the group of the element is also an influencing factor on the reaction. 1A metals, like sodium, tend to react better than 2A metals, like calcium, because they have a lower ionization energy. Ions also generally react faster than molecular compounds, because ions dissociate where molecular compounds either do not dissociate or need to have some ionization process to occur to break the bonds that are in the molecule. The smaller the pieces of my reactant, the faster the rate generally is. If I take salt, for instance, and grind it up into smaller pieces, it dissolves much more effectively than a salt as a large crystal, because the higher surface area allows more contact for the reaction to occur.